I did not. It worked. Look at that. Okay, welcome everyone to the 2025 NHFP Symposium. It's great to have you all here at Space Telescope. This is the second time we've had the full symposium here at Space Telescope, and we're very glad to have you here. It's also wonderful to have you all here in person. That's something we haven't always been able to do, but also come and enjoy yourselves here. We have lots of breaks and refreshments, so enjoy that. But use the time to meet the other fellows, talk to the other fellows, and form groups and collaborations and enjoy yourselves. Okay. There are going to be 55 science talks this time, and we're running off the bottom. Oh, let's see. It's not full. Let's see. Well, let's get it to. Double clicking, it doesn't do it. Let's see. Yep. Yeah, the view down here. Yep. Where's the bottom? All the way to the bottom slideshow. There we go. All right. I don't use the PDF version. So there we go. And that was too fast. So we have some special non-science sessions. We have the science policy today. Tomorrow, you'll have a chance to speak to the grants office and ask. It's just a question and answer session. Any questions you have about your grants, how to run them, questions about our policies. In fact, we often get some of the best suggestions on how the policies should change and what would be better for you all at this session. So think about that. Are there things that you think we should change that would improve the program? Let us know. Then on Wednesday, there's a professional development session. And then just before, I think just before lunch. And then on Thursday, yes, it's 12. And then on Thursday, the early career panel. Unfortunately, due to the government shutdown, Peg Luce won't be here, but we have Nino Cucchiara, who is the program scientist for the program for the NHFP, and he has some slides from her and from the director of astrophysics, and he'll give a short presentation today, and you'll see him again later on. And he's here all week, I think.
Today, tomorrow.
Oh, you're not going to be here at the end of the. You're not going to be here on Friday?
No, no.
Okay. That's a change then on the Friday program. All right. Well then, you speak to him all you can. He's a great resource, and he's been very instrumental in helping us get funds for the extra programs, the non-science programs, and some other things we'll tell you about later. And so, yeah. And Jennifer Wiseman, I don't know if maybe will show up if the shutdown ends by the end of the week, but given that the House is not in session, that doesn't seem too likely. Yeah. So, right. Okay, I'm Andy Fruchter at Space Telescope. Jen Burt, why don't you stand up, Jen? Yeah, is our Sagan lead, and Aneta Shimiganowska is the Einstein lead, right? And you probably met us all through email, but now, and maybe even 2D versions, but now you have the full 3D, and you can decide whether that's better or not. Okay. Okay, and Megan Crane is our program assistant lead. She's out in California and didn't come this time, but she's a wonderful person to get to know, and she's a phenomenal programmer and assistant. So yeah, and Sharita Hanna, who's outside and has done the logistics for this program and runs the events planning at Space Telescope. All right, we have Adam Smirchina, we have the NHFP SOC, and right, the SOC is made up of you, the fellows. So we have Adam and Alexander Dittman, Justin Pirel, Nicholas Rui, Sanskriti Das, and Sarah Moran. And let's give them a big hand. You guys want to stand? I don't know how many we have in the room. You guys, there's Justin. You guys want to stand up? And well, you don't have to if you don't want to. But you guys. But yeah, they did a lot of work, and thank them for this. It's very helpful. The leads appreciate it dramatically because before we had it as Fellows SOC, we had to do it ourselves. All right, there's a code of conduct, and I don't think, yeah, be good, right? Treat other people well. Treat them the way you would want to be treated. I don't know, that's a famous quotation somewhere, but I think if you do that, we'll all be fine. There are details here, right? Okay. Okay, and you should have uploaded. This is also pretty long, so please upload your talks the day before, so that we don't have to run around on the day. And just be at the beginning of each session, there's a chance to check out your slides. Please do that too, though I didn't do it, so I didn't. All right, I just had too much faith. Group photo tomorrow before the morning coffee break, and then the symposium dinner. That will actually be here. That's the first time we've done that. We'll see how it works. We brought in caterers here, and hopefully it'll be very nice. And yeah, we'll see. It's a new experience. Okay. But Caltech did something similar, though. You did it in a courtyard, which was very, but that's California. What can you do? All right. All right. Wednesday, you have a free afternoon starting at 1. Do you guys have signups online, I believe, right? Yeah. So go downtown. Justin is leading people to DC. I think Sarah's got a group that's going to the Visionary Art Museum, which is incredible. If you like art and crazy art, it's really bizarre. But it's because it's self-taught artists. It's all self-taught art, and it's really interesting. It can be, it's a constantly changing set of exhibits, so it varies, but some of the stuff is truly amazing. And then also there's another trip to the aquarium, which is, I think, even better than the Monterey Aquarium. So, and I thought that when I moved here from California. So yeah, so it's not like local pride. All right, Thursday, open mic with snacks and drinks at 8:30. All right. And yeah, and please, if you've got some talent, even if you don't have any talent, like me, I may do something and I haven't done it. Please, God, sign up for the open mic. Anything you'd like to do. We've had cooking demonstrations. We have had amazing musical performances. We've had poetry. Anything you want to do, we're interested in. Okay. And you can, and during the pandemic, when it was online and it was very intimate, people just told us stories about their lives that were amazing. So that too, just anyway, just whatever you'd like to do, up to 10 minutes, just do it. All right. We have masks if you are concerned, and you can be. I mean, apparently it's pretty high right now, so feel free to wear masks. And if you have any symptoms or are concerned about exposure, please get a test. There's a CVS around the corner, and we have a few here if you come in and you're not feeling well and you want to test. We have but it's only a few, so we can't. It's not like enough to hand out, unfortunately. All right. Any questions? Okay. If not, let's get started. Yes. Let's see. So next is, I think, is Nino, right? Oh, what's up there? Save no. Oh, what? No.
Save the date for next year.
Oh, right. Save the date. Oh, right. We did. You worked that out. Good. So it is official now. We have September 28th to October 2nd next year. Yep. Yes, and see if in okay, so you're doing it. You're doing in. Well, yep. Okay. No Hillel. No. Okay, great. So, yep. Cambridge next year. All right. Yeah. Let's see. Let me escape. Let's see.
Go back to your opening slide. Just leave that one. That's the one with
Which one did you?
The very beginning. Just.
You want my slide? One of these slides?
Yeah.
Okay.
Let's just leave that up there for a little entertainment.
Oh, okay.
There we go.
All right. Let me just do. Oh, I'll give you the whole thing then. Because you're going to do it spoken, eh?
Yes.
Oh my gosh, so old school. You're brave. You are brave.
That's
Okay.
right. Very old school. I don't have any slides to share with you because. Ooh. Okay, excellent. Right, because you all are going to have the fantastic slides throughout the week. I am Nancy Levinson. I'm the Deputy Director at Space Telescope Science Institute, and so it is absolutely my pleasure to welcome you all here for this event. This Fellows Symposium is really one of the highlights of the calendar every year. Because there are so many wonderful ideas that go on. You are such a fantastic group of people. There's a lot of energy, there's a lot of thinking, and it's just great to see what happens when you have the time to come together. I get the privilege of welcoming you because you're at my place, but obviously this happens because of a lot of others, and I know we'll get to hear from some of them as well. So NASA very broadly, the other centers that support these fellowship activities, the Chandra X-ray Center, JPL, and NextSci, as well as Space Telescope. And it's a really good collaboration. I'm really pleased with how we all work together, and we hope to support what is a great program. The most fantastic thing, of course, of what you're doing and what you're going to be doing here over this week is the science. Your work is touching on every fundamental aspect of astrophysics and planetary science. You're asking the really big questions, and I admit I have high expectations, many of us do, for you about the great discoveries and the real advancements that you will be able to make. That we really expect some significant progress, and also some of the work that you'll be doing to really elucidate those thorny issues that are underlying even some of the things that we thought we knew and we thought were pretty settled. This is such a great program. You have accomplished so much even to be here. As I think many of you know, that this is among the most competitive programs overall in astrophysics. It's got an oversubscription rate of 27-1. So you are special to be here. So glad to see you here. I want to say a few words about Space Telescope Science Institute and some of what we do here. Well, of course, recognizing all of the different institutions and the different facilities that you wind up relying on and using to do what you like to do. We are the Science Operations Center for Hubble, for Roman, and also for JWST, and JWST also includes the Mission Operations Center, which is right one floor upstairs. I don't know if you've arranged for a Good. Oh, okay. All right. Because there's a lot going on. You don't have a definite plan to see it, but I hope maybe we can arrange that some other time. And then we also have the Mikulski Archive for Space Telescopes, and those archives are so important because they really enable a lot of reuse and further discovery of the basis of so many of our NASA missions. I do want to say a couple of words about these different missions. First, for Hubble, the big take home is that this is still a vital and operating mission, that Hubble offers us some unique capabilities, especially in the ultraviolet and in the visible. And it also gives us the truly long time baseline. And we've been seeing some recent discoveries taking advantage of that really long time evolution to look for those changes. I know much of the time we think about transient phenomena, changes as a short-term fact, but there's also a very, very long-term fact. And so Hubble is continuing to operate well. And really, our lifetime limiting factor is the orbit, the altitude above that's where the Earth's atmosphere gets in the way and is bringing us down a bit. But otherwise, performing very well and really able to do a lot of what we want to do. For Roman, we are all working towards a launch of September 2026. That's less than a year away. That's accelerating not only the NASA commitment, but even what the planning had been as of 6 months ago. That we really want to get this literally off the ground and start taking data and doing great things with it. And Roman is going to be new for NASA astrophysics as a big data mission. And also that's going to mean for us as scientists different ways to work with this mission. Some of you may have experience with other kinds of observatories, other kinds of programs like this. But again, for a NASA flagship astrophysics, this is new. And so instead of our Hubble and JWST mode, a little more artisanal and downloading to our own private computers and working on the data, I admit that's how I work a lot of the time. We're really going to have to interact with the catalogs, with the science platforms, to go to the data and work with the data there. And so that's something that Space Telescope, along with our colleagues at IPAC and at NASA Goddard are working on, is really to offer those kinds of capabilities, so that it's not a matter of being at an exclusive or privileged organization or having your own private access to resources to be able to work this way, but we want to offer that to you. This is really building on so much of what we do generally with archives, but this is really the starting point for so much of it. There are core community surveys that are defined, and while those have specific science goals, related to dark energy, related to exoplanets. They're going to be large surveys of the sky, and there are going to be a lot of different things that we will all be able to use those observations for. They will be extremely well calibrated, covering wide fields, and so that's where we're looking for opportunity to use the data with those plans that are already being made. And there is the possibility of independent programs for new observations. But a real shift in mindset for many of us is that even those new programs, they're still big surveys. That's just the capability of Roman with the wide field. And so those will be the most valuable and most informative kinds of programs. So we're working hard on this today and looking forward to what's happening with Roman, and I hope that some of you see your science cases and see good ways to use that in the future. And of course, there's JWST. I mean, I continue to be astounded at what is happening and what we as a community are learning based on these new observations, that we as a community are really finding transformative science across the whole range. Incredible discoveries about exoplanets and their atmospheres, really studying the evolution of galaxies, and then going back to the early universe and just observing things that we haven't seen before, and that's informing what we do. It's informing our theory, it's informing our future observations. And we really have an opportunity now, I think, to having done a lot of the small scale initial tests, initial investigations, to now become more systematic and to really think, how do we draw robust conclusions? How do we have significant samples that let us draw bigger conclusions about what's going on? And I think there's a lot of opportunity there for that kind of thing. Just on a personal note, I'll add that for my own field, active galactic nuclei, in some ways, I think that JWST has not only refreshed the field, but reconnected us with a lot of other work that was going on. You might argue that a number of years ago, AGN were kind of off in their own little domain and talking amongst themselves, but now I think we're really, really connected. I think there are those kinds of connections in other fields as well. So that's personally exciting for me. So, of course, I'm sure all of your JWST Cycle 5 proposals are already submitted, because after all, the deadline is soon after this symposium. But in any case, there may even be some fantastic, okay, I'm laughing, my proposals are not submitted, so, but there may even be some fantastic ideas that emerge out of this that turn into something, if not Cycle 5, for Cycle 6 and beyond. That we're certainly looking forward to a long lifetime for JWST, and I hope that there's motivation here. So it's not just JWST, and it's not just any one mission in isolation. One of my particular areas of focus, and I would say for Space Telescope overall, is to think about multi-mission opportunities. And so I know many of you are already doing that. So even beyond these missions that I've been talking about, but integrating X-ray observations with Chandra or other kinds of capabilities, and of course theory and laboratory work as well that are so important. But really thinking about, how do we synthesize what we're doing across missions? I think astronomers are great about grabbing the tools that they need to answer specific questions as they come up. But I find that a fair bit of that is still done in what I might describe as a multiple mission kind of way, that you take different pieces from different areas. And so really thinking about, how do we make use of these capabilities together, whether it's space or ground or elsewhere, or other kinds of techniques, but to really use them fully. And so this is an area that I genuinely welcome your thoughts in this kind of direction of, where do you see scientific opportunity for this multi-mission kind of work? And also, are there ways that we as Space Telescope, with the missions we organize, or the other centers and institutions that support other areas, are there things that we could do differently to help you make those kinds of discoveries that you would like? And then as Andy had mentioned with the program, we've got a number of non-scientific sessions that I think will be really, really interesting. I mean, I know the SOC put them on the program because they are of interest. And what I do want to call attention to in particular is the discussion of policy, which in our environment, we here in Baltimore feel ourselves a bit close to Washington, D.C. sometimes, maybe a little too close in some ways. But it really is important. We in astronomy and planetary science are really fortunate in that we've maintained broad public support for what we do. And what we are trying to do, the kind of science we do, the kinds of resources that we need, those are big resources. Those are expensive things to do. And we really do need that public support, whether it's at the state or the national level, to do that. And so the science discoveries that you're making, that is absolutely the starting point. But the science itself is not sufficient to get us to where we want to be, to have these facilities and have these opportunities that we would like. And so for those of you who are inclined this way, I do encourage you to share what you're doing, share your stories, share your discoveries, and make connections about what you do even beyond the very specific of what you do. And that can appear in a number of different ways. It might be that you're active on social media and you share with that group of followers that you have so other people can learn about it. Maybe you have a particular discovery that warrants a press release or other kind of publicity, and that might happen through your home institution, or it might happen through some of these other more formal institutions of the observatories. But that's something that ultimately is valuable. I personally believe that our real drive for discovery and discovery of the universe and the inspiration that it generates, those are public good, but good as long as we truly make them public and that we get beyond the conversations among ourselves to draw those connections to the public. So we're recognizing that's not everybody's motivation, that's not everybody's comfort zone, so it's not a call to action on everybody. But if you're there and if you're comfortable with that, and I think with this policy discussion, you might have some good insight and advice about how to be effective as you do that. So I am going to close out here to give us some more time for some of what's the really important stuff about what we're here for this week. But just in closing, my main messages are welcome to Space Telescope Science Institute, and thanks so much for being here. And I'm really looking forward to a great week. And also, I'm happy to take any questions if you have them, and if not, we'll carry on. Any questions now?
First question is always the hardest.
This is not shy. Come on. Yeah, let you go. Or if not, I'll try to drop in for some of today. Unfortunately, my time, especially today and tomorrow, is a bit more limited, but still looking forward to all of what you're doing. So thanks so much for being here.
Thank you. All right. Shutdown lesson 101, when no government employee can work or can participate in anything, so you got me. You're lucky because I'm a contractor, and my name is Nino Cucchiara. I am the program scientist for the NASA Hubble Fellowship Program, working closely with the leads, former leads. My colleagues at headquarters, Hashim Hassan, Pak Nazek, unfortunately just rolled off, and many people has at Goddard, Jeffrey Wiseman, Pat Krause, and so forth. So I'm going to apologize for the first speakers. I'll try to be fast. As you see here, I managed the Hubble Fellowship Program, which but also manage the Finance Program, which is a research grant for graduate students, as well as I'm a time domain astrophysics, as well as a Fermi mission program scientist. So a little bit of all the buzz for the last year about funding, NASA, whatever. As we said, as Nancy said, the NASA Hubble Fellowship Program is the most prestigious fellowship in astrophysics and is recognized around the world. Okay, you have incredible new ideas. You're really bringing the field forward, and we're really grateful for that. Many of you, and I know that for a fact because we look at the 900 of previous years, will be leadership positions. That means the directors, center directors, directors of observatories, deans, chairs, and presidents, I don't know. Anyway, you'll have this great future in front of you, and that's what this program is. Great, paving the way for these amazing accomplishments. The program was reviewed in 2021, and I want to confirm this on behalf of the Astrophysics Director, Sean Domagal-Goldwyn, Deputy Director Peg Luce, and the whole Astrophysics Division at NASA. This is our cornerstone investment on the future of workforce in astrophysics. The program is healthy, is well-funded, will be well-funded, nothing to be worried about, at least you, nothing to be worried about. And please, I'm here for you. Personally, I'll be here for the next couple of days. I'm leaving Wednesday morning to go back to California. But if you have any question, any idea, bring it to me or the leads. They're here with you, and we'll try to make the program better and improving as much as we can. We will continue to improve it based on the decadal survey recommendation, the review, but also the NASA as an agency and their priorities, okay? Nancy already mentioned this. She kind of stole the thunder from me. This is a very graphic of what the Hubble Fellows do. The Hubble Fellows do things across the spectrum of astrophysics, across wavelengths, and theory and technology. I'm not going to list them all, but this is all research done by this class, in the past 3 years. So as you can see, it's not one mission, as Nancy said, but it crosses essentially the entire astrophysics division, and that explains why you are so important to us, and that's why we continue to fund this program. Again, as I said, the program was reviewed. There were several recommendations. We want to make sure that the program continue to be successful, but also we want to align the program to the new recommendation that came out from the decadal survey, right? We cannot separate the science from the individual who make the science. That's from the chapter of the state of the profession. And we really take that and embrace that heartily and really want to make this part of that, the changes, right? And so I want to move forward here. And this is one of the recommendations from that NHFP report was, where is the mission statement? I'm going to read it aloud for you in case you don't know. The NHFP Fellowship Program fosters excellence and leadership in astrophysics by supporting exceptionally promising and innovative early career astrophysicists. And here I want to highlight in red here the excellence and leadership, because leaders for us means multiple things, and that's where we are moving away and forward, I should say, from the past idea. Leaders are researchers who provide these new discoveries, you do publications, and you're recognized as leaders in the field, right? You're team leaders. You are role models, because the way you do research is a lighthouse for the undergrads, the graduate students that are below you. They see you, how you do the research. You're collaborating. You have collaboration around the country. You are collaborating internationally, right? And everybody recognizes you for who you are. And you set the gold standards of success for postdocs. Yes, I'm sorry, but you are the elite of the postdoctoral scholars, right? And now we want you to also be reliable mentors, right? Someone that is trained to be a mentor. Mentor is not someone that is born to be a mentor, right? So we want to train you if you need to be trained, right? You will be mindful of the mentor-mentee relationships, and we want to be sure you're able to advise students and mentees in the research, the academic life, but also their life choices, their career path. Understanding that the students you have in front of you might not want to be an astronomer. That's fine. That is fine. So accepting that reality and helping the students moving forward in what they want to be and not what you want them to be is a critical path. And finally, a representation of who you are, your communities, where you came from, your history, your educational background, because that is important. The person you have in front of you, whoever it is, will see you for who you are, but sometimes we hide that from them. I am that person that published 50 papers a year, and that's it. I am the person that study AGN, and that's it. But that's not the end of the story. That's what we want you to be. We want you to be that full persona, not just the researcher and the face in front of those publication records or H-index. Okay, last 2 slides for you. Again, this is to reiterate that we want you to be NASA ambassadors. We want to showcase the amazing science you do, and most importantly, represent who you are and you came from. Okay, and represent essentially role models for all the students in the country. And then very briefly, some of you already seen this. We spearheaded this idea of NHFP on tour, where essentially we want you support, in case you are interested in doing something like this, to engage with faculty and students around the country, either through virtual or in-person presentations, and where you can showcase your research, but also everything you've done in your past, your undergraduate stories, your community college story, or your R1 institutional stories, right, good or bad, and tell everybody who you are. So we started this program, this idea that came out in March or April. It had 24 institutions, and I want to thank you for all of you who already filled half of those spots. Again, this is not a request, or is up, if you really feel like, please reach out to me. I know some of you have already responded. More than happy to make those connections. And if you're interested in sharing your stories with other schools and other institutions you might not think about, like small schools, R2s, and community colleges that might be near your host institution. Okay. All right. I'm not going to say anything about the other thing that Andy was mentioning, because I don't want to steal the time from the leads, if that's something that we can come up later. But anyway, I'll be here, so I don't want to take questions now. But I'll be here during the coffee breaks and lunch and so forth. So if you want to talk to me, you know where to find me. So we can get started with the speakers. And these are my email addresses. Thank you, as fast as I could.
The chair.
Who's the chair?
What was the first chair?
Let's see.
Okay.
First speaker is Kenzie.
Who's the first speaker? She's there. Yeah. Okay, go. You're good.
This is for you.
Thank you.
I'll give you
412.
Before 12 minutes or before 15?
412.
Before 12. Okay.
Unless you want.
Yeah.
Cool. Okay, does this work? Yeah, okay. All right, thanks for being here, everyone. All right, so our first talk of the day is by Kenzie Nemo, telling us about FRBs and their local environments.
Cool, thank you. Hi, everyone. I'm Kenzie Nemo. This is my first NHFP Symposium. So I'm very happy to be here and to be telling you about FRBs this morning. Let's get into it. So if you've never seen an FRB before, this is an FRB. This is the first ever discovered fast radio burst. And it's a millisecond duration radio transient that swept from high frequencies to low frequencies, as you can see here. This is due to an effect called dispersion. So as the radio waves propagate through ionized plasma, they get this frequency-dependent time delay. And it's proportional to this DM, or dispersion measure, which is the integrated column density of electrons along this path. So you can think of this like a proxy for distance. The farther the radio waves travel, the more electrons they interact with, the larger the DM, the larger the time delay. And this wasn't what was surprising about this transient when it was first discovered, because we see transients like this from galactic pulsars. But because we see transients like this from galactic pulsars, we have a relatively good map of electrons in the Milky Way's interstellar medium. And what was surprising about this transient was that only a small fraction of the observed dispersion was thought to be coming from electrons in the Milky Way's interstellar medium. The interpretation then was the rest of this was coming from electrons in the intergalactic medium, maybe a host galaxy, implying that this transient was extragalactic. And that means that it must be incredibly luminous. Here I'm comparing pulsars with FRBs. They occur on similar transient timescales, millisecond timescales, but FRBs are more than 10 orders of magnitude more luminous. And so that begs the question, what are they? What kind of objects are producing FRBs? There's lots of theories out there. The most promising theory is magnetars. Reason is because back in 2020, a known galactic magnetar produced an FRB. And so that was very compelling evidence that at least some of the FRBs that we detect are coming from extragalactic magnetars. However, we see a huge diversity in the FRB population that aren't reflected by what we see from this galactic magnetar. We see repeating FRBs with a range of activity levels. Most of them don't repeat. They produce one burst and never again. We see ranges of timescales and spectral properties and polarization properties. And there's a huge debate in the field right now about whether or not this kind of like one model fits all is the solution, or whether maybe there's different types of objects that can produce FRBs or different physics involved. And so to tackle this question, the key is really in looking at where these FRBs are coming from. Reason being is we can draw an analogy to other areas of transient astrophysics. So in the case of gamma ray bursts, they were classified as long and short GRBs based on their temporal durations. And then later they were found in very different environments. The long GRBs are found in low metallicity environments, linking them to the death of massive stars. And short GRBs are found in the far outskirts of galaxies, linking them to compact binary mergers. So we want to play a similar game with FRBs. But first, we need to be able to pinpoint FRBs to their environments. So to do that, we use a technique called very long baseline interferometry. The idea here is we have radio telescopes, we separate them at very far distances from each other, and we cross-correlate the signals from these telescopes to achieve very high angular resolution. And the resolution goes as the wavelength over the baseline or the telescope separation. And for a telescope like the European VLBI network that I'm showing here, we have baselines of like thousands of kilometers, and that gets us to milliarc-second resolution, which tells us not only the host galaxy, but also where in the host galaxy these FRBs are coming from. And through my PhD, I localize repeating FRBs to their local environments using this technique. And we found them all over the place. So we find FRBs that are coincident with active star forming regions, which you would expect if they're young objects like magnetars. But we do find some kind of interesting ones over here. This FRB here it looks like it's on top of this star forming region, but combining the high resolution radio with this beautiful HST image and the high resolution that we can get with Hubble, we actually can measure an offset from the nearby star forming region, implying that it's an older source. And then on the far end of this spectrum here, we have an FRB that's in a globular cluster. And so if it's a magnetar that was created through the core collapse of a massive star, we certainly wouldn't expect that to be living in an old stellar population like a globular cluster. And so it begs the question, are these really all magnetars? Or are there different beasts underlying this population? But the keen eye in the audience will have noticed I'm only talking about repeating FRBs here. And they represent only about 3% of the total population. So this is definitely not representative of FRBs on a whole. The limitation here is that telescopes like the European VLBI network that I showed on the previous slide, they have very small fields of view. And so we can't find new FRBs with a telescope like the EVN. We can only point at known sources and wait for them to produce another burst. And so we've been kind of limited to the repeating FRBs in these kind of studies. However, on the non-repeaters, there exist connected interferometers like ASCAP and DSA 110 that have been able to get kind of arc-second scale localizations, which lets us tell the FRB host galaxies. Doesn't really give us local environment information, but this is telling a somewhat different story than the previous slide. Here, both of these studies are finding that the FRBs are tracing star formation. So they don't see the same diversity that we see for the repeaters. However, we're not comparing apples to apples, right? These are the host galaxies, and previously these are the local environments I'm talking about. And if I highlight these two here, if you look at their host galaxies, they're pretty normal star-forming galaxies. So it's really important that we can probe FRBs on the local environment scale to get this complete picture of the underlying progenitors. So we need a telescope that can find lots of FRBs, but then can also pinpoint them to VLBI level precision. For the former, we have a telescope called CHIME. I'm a member of the CHIME collaboration. This is a telescope in Canada, and it's designed to have an incredibly large field of view, 200 square degrees field of view. And it turns out that this design is perfect for finding FRBs. Here, this is I'm showing the cumulative number of FRBs as a function of time. In pink is all telescopes on Earth combined, excluding CHIME, and in blue is CHIME only. And you can see when CHIME turned on, it only took a few months for it to totally dominate the field in terms of number of FRBs. And at the moment, we have about 5,000 FRBs. This is a log scale. So yeah, CHIME really is like the world's best FRB finder. The problem with CHIME is that when we find an FRB, we know its position to, at best, an arc minute, which here on the Hubble Deep Field, you can see there's just lots of stuff in an arc minute. And so we don't really get, for most CHIME FRBs, we don't really get any information about the galaxies that they're in or their environments. So over the last few years, we've been building the CHIME FRB outriggers. Essentially, we're building many versions of CHIME across North America to turn CHIME into a VLBI array. And so when we detect an FRB with CHIME, we can pinpoint it to sub-galaxy precision. And this telescope has been fully operational from about like February or March of this year, which is great. But yeah, for the last few minutes of my talk, I want to go through some of the early science that we've been able to do with this instrument as we've been building. So we built each of these mini telescopes one by one and added them one by one and commissioned them one by one. And as a result, we have some steps in the science. So one of the first things that we did was we actually localized a repeating FRB to the far outskirts of a massive elliptical galaxy that you can see here. So this is kind of like doubly quiescent, right? The far outskirt is one of the largest offsets that we've seen for an FRB from the disk. And then also, this galaxy is a massive elliptical galaxy, which adds to this complicated picture. And yeah, this adds even more diversity to the repeating FRB environments that I presented earlier. And yeah, I guess it also begs the question, if this really is a magnetar, what is it doing all the way out here? Also with this first outrigger, we published our first outrigger host galaxy catalog. This is a sample of 20 host galaxies for mostly non-repeating FRBs. You can see a bunch of spiral galaxies. There's quite a few pairs of galaxies and a merger, galaxy merger. So we're already seeing quite a lot in this very small sample of local universe FRBs. And we're in the process of characterizing these host galaxy properties as part of a larger sample, as well as combining that with the radio properties of the FRBs to explore if there's different types of FRBs and different types of galaxies, for example. After KKO, we then added our longest baseline into the array. This is the GBO telescope in West Virginia. And you can see the improvement on the localization by adding this baseline. So we've gone from the white ellipse here to the orange ellipse, which I've had to zoom in on to really emphasize. So this is us getting to 50 milliarcseconds, which is the spec of this telescope. And that lets us really go from galaxy scale in white to sub-galaxy scale in orange. And this was a repeating FRB, so we were lucky that it produced another burst after we added GBO, so we could do this nice comparison. And yeah, like I said, we're actively working on the next galaxy catalog for basically everything that we've detected before we turned on the full outrigger system. And so yeah, stay tuned for that, it's coming soon. And then we were extremely lucky that when we turned on our full system, we discovered the brightest FRB that we'd ever seen at CHIME, and we detected it at all of our outrigger sites, meaning we could get a full outrigger localization of this really unique FRB. We're calling it RB Float, which is the radio brightest FRB of all time, I think is the acronym. But yeah, it's super bright because it's super nearby. This is only 40 megaparsecs, which is pretty nearby for FRBs. And you can see in the zoom in, this is our localization. So the red 1, 2, and 3 sigma contours, which we can see that it's very close to this H2 region in the galaxy, but measurably offset from the H2 region. This offset could imply that it's an older source, right? That it's not quite associated with active star formation, but more on the outskirts. However, we did some deep JWST imaging of the FRB site that uncovered a bunch of a bunch of near infrared emission coincident with the FRB position. And so with this deep imaging, we can see that that it's totally reasonable that there could be a young magnetar here consistent with a young stellar population that we see in the JWST image, which is really beautiful. And it also shows the uniqueness of combining the high resolution that we can get with the outriggers with the high resolution that we can get with JWST to really probe what's happening at the site of the FRB, the immediate site of the FRB. And I'll refer to Aaron's talk, who's after me, who's going to talk about RB float in more detail. So I think I have a minute left. So what have you got to look forward to? That's just one non-repeating FRB environment on kind of 10 parsec scales, but we've been actively detecting like 5 FRBs a week with the outriggers, and so we're very quickly accumulating a sample of FRBs with VLBI localization that we can start to tackle these big questions in the field, some of which I talked about. So what kind of FRBs what kind of environments are these FRBs living in? What does that mean for their progenitors? Are there different types of FRBs that live in different types of environments? Do the non-repeating FRBs show the same diversity in environments as the repeating FRBs? We're also searching to see if the FRBs are co-located with other known transients. There's theories to expect they should be coming from supernovae or GRBs. And then finally, once we have redshifts and galaxies, we can also probe using the radio properties what kind of magnetic fields and densities are existing in these extreme compact object systems. With that, I'll take any questions. Thank you very much.
All right, questions?
This is so cool. I'm blown away that you can localize, a star forming region where one of these things went on. So that JWST image you just showed in the last slide, there's the source there, right? NIR1 or whatever. Do you know anything about this star? Have you thrown it up on a magnitude diagram? Do you know what type of star you're probably looking at in the middle of this image?
There's a few theories about what NIR1 could be. The issue is that the probability of chance coincidence is not great. So we can't say for sure that the FRB is associated with NIR1. I think the most conservative thing to say is that there is a young stellar population consistent with the position of the FRB, and so it's possible that it could be a magnetar. However, there are other theories that could link it to something more evolved through these NIR observations. But the probability of chance coincidence kind of kills you.
Question right here.
Great talk. If I understand correctly, so you found something with chime, you don't know where to point, so there you go with the outriggers, right?
Not quite. We are observing the same part of the sky at all times with chime and the outriggers. So when chime detects something, it sends a trigger to the outriggers and it dumps the data, and then we cross-correlate.
So what's the latency between the chime detection and the data taking from the outriggers? Because they're very fast. So
yeah, there's no latency or minimal latency. We use the fact that there's like a time delay because of how far apart these telescopes are. But the trigger is essentially instantaneous. So most FRBs, unless their dispersion measures are really high, that's when we start to hit an issue because the sweep takes a lot longer. Unless the dispersion measure is really high, then we catch most bursts that we detect with chime at the outrigger sites. Yep.
aren't you always taking data with the outriggers, then you just save the data? Or no?
There's a buffer, yeah.
Exactly, so that's why there's no problem with this, because you're always taking the data, they just save the data. Yeah, I guess that they have the same field of view, right?
Yeah, they have exactly overlapping field of view. So the outriggers can see everything that chime sees, and then there's a buffer that once we get the trigger from chime, we write to disk the data. Yep.
The ones that don't, the ones offset visually that you showed us.
Yeah.
How deep are those images?
That's a good question. This image, I can't remember off the top of my head. They're pretty deep, but are you alluding to like a globular cluster or a satellite? Or
So early on with GRBs, people would assume that deep offsets meant it was just offset from the disk because they could see something.
Yeah.
But then you do deep observations and you find, well, there's a separate galaxy, a faint galaxy, right, that's much more distant or smaller. So can you rule out a much more distant or smaller thing from the dispersion measure, or is it possible that you're actually you're looking much further and there are more galaxies that you can pocket rich?
Yeah, I mean, this is an open question for this source. We've tried to get JWST time, but haven't been successful yet to do a deep image here, a deeper image here. What I will say is that when we are associating FRBs to galaxies, we have this like probabilistic association framework, and so based on that, it's really unlikely that it's not associated with the massive elliptical galaxy, just on the probability argument because of how well we've localized the FRB. However, we have entertained the idea that there could be like a satellite dwarf galaxy at the same redshift, or which we explore with deep imaging. I think it's unlikely that there's a background galaxy, but we could be wrong.
Okay, we have to move on. Let's thank Kenzie one more time. All right, next up we have Aaron Perlman, also talking about FRBs and CHIME. I don't know. Okay, I'll give you 2 minutes.
Okay, thanks. Okay, hi everyone. My name is Aaron Perlman. I also work on the CHIME FRB Outriggers project along with Kenzie. This is my first Hubble Symposium, so it's great to see everyone, and thanks to the organizers for preparing the meeting. I'm going to be an incoming Hubble Fellow at MIT, and today I want to build upon Kenzie's talk and tell you a bit more about some of the technical details about how we do outrigger localizations and how we're going to get many of these high precision FRB localizations, and also some of the astrophysics that's going to come from that. So the first thing I want to point out is that the CHIME FRB outriggers experiment, the VLBI experiment that we run, is not a traditional VLBI imaging experiment. So we pioneered a new technique called synoptic transient radio VLBI to basically localize these short duration impulsive signals by cross-correlating data from just a few baselines. So we have very little UV coverage, but we really only need 2 delay measurements in order to measure the RA and declination positions of the source. And what this requires is that you need to basically know very well the behavior of the clock, your ionosphere, your instrumental and telescope positions. If you can characterize those very well, then you can measure a delay, and that then translates into a position of the FRB. One of the major challenges that I work on personally is trying to push the astrometry to as high precision as possible. So we want to localize thousands of these FRBs with 50 milliarcsecond precision or better. And the challenge is that we don't know when or where on the sky the FRB is going to be, and we need an always ready calibration solution. And this requires understanding things like the ionosphere, the clock, etc. Okay, so the CHIME FRB Outriggers project is really kind of the first wide field low frequency VLBI experiment on long baselines. And what we've had to do to basically get calibrators that work for our experiment is to do a calibrator survey. So what we use right now is these compact continuum radio calibrators that happen to be in our beam when we detect the FRB, and then we can basically phase reference the visibilities and derive a position for each FRB. We're also planning to supplement this with compact radio pulsars, because we know on the long baselines, radio pulsars are going to be compact, right? Neutron stars. Okay, so so far what we've done is we've used pulsars basically as mock FRBs, and we can basically use them to test our astrometric precision. So what I show here on the bottom plots is pulsar localizations done by a graduate student at MIT, Shion Andrew, who has cross-correlated these pulsars on each of the different baselines, CHIME and GBO and CHIME and HCO. And what you can see is that for really high signal-to-noise pulses, we can get to 50 milliarc seconds. And you also notice that depending on how far away our VLBI calibrator is from the FRB, or in this case, a test pulsar, the astrometry gets worse, right? So this is basically explained by the fact that as the telescopes are looking through different parts of the ionosphere, there's an ionospheric delay that's wavelength squared dependent. And as you move further away from the calibrator, the telescopes see different contributions from the ionosphere. And this is difficult to characterize, right? There aren't really good models that allow us to understand the ionosphere. So we try to basically mitigate this by having calibrators that are really close. And this is the challenge with this experiment is how do we get these really precise FRB localizations and also calibrate really well and get these calibrators really close on the sky? So this is the part that I work on. So the solution is I've been building these tide array digital tracking beams. These are beam-formed, basically beams that track different calibrators across the sky. And we're always observing or plan to always observe these calibrators. And when an FRB goes off, what we do is we save the VLBI data so we can go back and cross-correlate it with the FRB. And the idea is that we want to have a calibrator before and after every FRB, close on the sky and close in time. And we can also, because this has a much longer buffer, we can do much longer integrations and improve the signal to noise of these calibrators by a factor of 10 or 100 times. And we'll also be able to go really deep and get calibrators that are within 1 to 10 degrees of every FRB. And the way this works, this alludes to a question that was asked earlier. How do we do this in practice? Right, so the FRB experiment, when we detect an FRB, we save the phase-preserving electric field data, which contains the FRB, and then a trigger is sent to our buffer to save that data to disk. At the same time, we also send a trigger to the outriggers, and the corresponding FRB data that's also captured by the outriggers, which is observing the same field of view at the same time, is also saved to disk. So then how does the calibration system fit in? The idea is that we have a separate tracking beamformer that is always observing in tandem with the CHIME FRB outriggers experiment. And when we receive a trigger, then we save the calibration data to disk. And this is a system that's under rapid development right now. And I think I project will really enable us to get to really high precision FRB localizations. Our spec is 50 milliarc seconds, but we hope to do even better than that. Right. Okay. So if you really want to understand, I think, what types of individual sources make FRBs, then I think you can learn a lot from local universe FRBs. These are the FRBs that are the most nearby in the universe. With high precision localizations, you can really do a huge number of things as far as probing for multi-wavelength counterparts, understanding their local environments, and so forth. And FRBs traditionally have, even today, really been primarily a radio band limited phenomenon. So many people have looked across the electromagnetic spectrum, and there's still not really convincing evidence for electromagnetic counterpart for an extragalactic FRB. Right, and as Kenzie explained, there's really a lot of motivation to think that at least some fraction of magnetars produce FRBs. And we also know magnetars also produce a high and wide range of high energy and X-ray and gamma ray emission, because we see this from galactic magnetars in the Milky Way. And in principle, if you had a sensitive enough X-ray telescope or gamma ray telescope, you should be able to detect these things from FRB sources in the local universe. Right, and we've seen this in the one case where we've detected an FRB-like radio burst from a galactic magnetar, STR 1935. That was accompanied by a short X-ray burst, almost simultaneously with the radio burst. So this gives us a lot of confidence that FRBs, if they are magnetars and they're nearby, they should also produce detectable X-ray emission. Right. So let's turn our attention back to this FRB 2025-0316A. This is RB float. As Kenzie explained, this was a FRB that turned out to be extremely bright in the chime band, and we happened to localize it to a nearby galaxy, NGC 4141 at 40 megaparsecs, which also happened to coincidentally have some type 2 core collapse supernovae next to it. So one of the things that I wanted to also highlight is one of the reasons we were actually able to get such a high angular resolution on this FRB source was because we had calibrators that were very close on the sky at the same time as the FRB. And that really allowed us to drill down on the astrometry and get to around 50 milliarc-second localizations, which is probing the 10 parsec local environment of the FRB. Right. As Kenzie explained, we did deep James Webb follow-up of the field, and there were a number of IR sources that were detected with this candidate NIR1 falling in the innermost region of the FRB localization. So I wanted to talk a little bit about what the implications are for that, if under certain assumptions, right? So one thing is, if you expect FRBs to be associated with magnetars, you have a couple of good things going for you, right? You have massive star-forming clumps, which probably are comprised of young massive stars. These are the stellar progenitors of magnetars, so that's a good thing. But the IR emission that we detect for this NIR1 is perhaps a bit too bright compared to galactic magnetars. So we expect the IR emission from, we do see IR emission from galactic magnetars, but it would be below even the Webb sensitivity threshold. So this NIR1 candidate, as Kenzie was saying, it's not definitively associated with the FRB, but it could be some type of evolved giant star that's undergoing common envelope mass transfer, or it could be a very massive main sequence star. Another possibility we entertained is that as the amount of energy that was just emitted from the FRB itself was enormous, there could be some reprocessing of that energy in the dust, creating a dust echo. But nevertheless, magnetars, neutron stars, and stellar binaries are also viable options, right? And I wanted to highlight another example where you can go kind of another direction in the multi-wavelength follow-up. So Kenzie introduced this FRB 2020-0120E. This was an FRB that was discovered by CHIME. It was localized to sub-arc minute precision, but then it was subsequently localized even better by an ad hoc array of radio telescopes comprising the EVN to 1.3 milliarc seconds, and it was found to reside in a globular cluster, right? And globular clusters don't have many massive stars, and that goes kind of counterintuitive to what you might expect for a magnetar. There are some explanations that suggest that you might be able to form a magnetar in an exotic way through accretion-induced collapse, but it really kind of flies in the face of the traditional galactic magnetar environment that we expect. And what we did was we also went after it with really sensitive high-energy telescopes like NICER Chandra XMM, together with really sensitive radio telescopes like Effelsberg, and tried to detect the expected X-ray emission that you might expect if it were, say, some type of analog of a galactic magnetar. And what we were able to do, we didn't detect any emission, but we were able to improve upon the X-ray energy limits at the time of radio burst by something like 4 orders of magnitude compared to all other measurements done in the field on FRBs. And also with deep Chandra observations, we were able to probe down to X-ray luminosities below that of the Crab Nebula of about a little bit below 10 to the 37 ergs per second in luminosity. And some scenarios that are disfavored or ruled out based upon this analysis are things like giant flares, which are some of the most violent events produced from magnetars, intermediate flares from magnetars, such as ones like the magnetar that produced an FRB-like burst, ultraluminous X-ray sources, and another class of X-ray transients called ultraluminous X-ray bursts. It's really kind of pointing to maybe a magnetar formed in some exotic scenario, like some type of merger or accretion-induced collapse, or perhaps a supergiant emitting pulsar. And then just in the last couple minutes, if you got bored of trying to figure out what FRBs are, then I apologize. But you might ask, well, what can FRBs do if you care? If you don't care at all what makes them, right? So it turns out that FRBs, as Kenzie was describing, has this remarkable property called dispersion, where the material through which it propagates, it has this characteristic delay in radio frequency with an index of refraction that's proportional to wavelength squared. And what happens is that as the radio wave propagates, it picks up an imprint of all the baryonic material through which it travels. And you can use FRBs to do cosmology. So this is an example from a seminal paper by J.P. McQuart, where they took a sample of FRBs and were able to basically separate the contributions from the dispersion measures. So this is the extragalactic contribution. So this is removing contributions from our galaxy and the host. And they were able to basically show that that the expectations of what you might expect for material traversing are consistent with what you derive from the FRBs. And in the past, some of the material that that is intervening at large distances is difficult to detect because it's diffuse. So this is the so-called missing baryon problem, right? So it's not that the baryons are missing, they're just difficult to detect. So you can use FRBs basically as a tool, a cosmological probe of things like astrophysical feedback, large-scale structure, and baryonic material. And this is really allowing you to then derive insights into how ordinary matter might interact with, say, dark matter halos and so forth. And I just want to highlight that, this is very early for our group doing this FRBs as cosmology type of work, but we have a few papers that have come out this year. I'll just point them here. So we have a paper now that takes the catalog we have a large catalog of FRBs, about 5,000 FRBs, and cross-correlates them with the DESI catalog. And we see some evidence of statistical significant cross-correlation, spatial cross-correlation between the FRB DMs and the galaxies. And also probing the intercluster medium, the intergroup medium, and FRBs from galaxy clusters, and looking at host DM and stellar mass relations from FRBs. And if you're interested, I'll point you to those papers, and then I'll leave my summary and outlook up and thank everyone and take questions.
All right, fantastic talk. Okay, questions for Aaron. Raj.
Thanks, great talk. I was curious with all of these local universe FRBs, do we have an understanding for what their volumetric rate is? Is it comparable to the core collapse supernova rate? And the related question is, within like a 10-year baseline, how many FRBs do you expect to be detected nearby enough that you can get constraining X-ray observations?
Yeah, okay, so this is okay, so a couple things. So first question, remind me, this was how many FRBs you expect in the local universe? Just
yeah.
So it depends on what your assumptions are for the cutoff energy, but let's take something like an RB float-like thing, like 10 to the 39 ergs. It would be probably on the order of around 100, maybe a little bit more per year that you would expect to detect across the whole sky.
Yeah. How many of them would be close enough that you can get X-ray constraining?
So I didn't show this. So with the current instrumentation that's available, like Chandra XMM, this is hard, but I have some backup slides. So there's a probe class mission that I'm excited about called Axis. And it's basically a super Chandra. Sorry, trying to go back. And with modest exposures of like 100 kiloseconds, you can get down to 3 times 10 to the minus 7 ergs per centimeter squared per second in flux. And when you try to translate that into how far out you could see X-ray emission from magnetars, it turns out you could probably see out to 50 megaparsecs for the persistent emission. And even with this this telescope, it allows you to do it quite a bit better in terms of detecting prompt X-ray emission. So if you were to say be interested in prompt X-ray bursts like the one from SGR in 1935, you could probably see it out to about 10 10 parsecs around there, 5 to 10 parsecs would be kind of my estimate based upon the sensitivity. And this is a mission that's currently under consideration. It will be, if it's selected, it would fly in 2032. So that's within your 10-year horizon. So I hope there'll be many of these things that will, be able to localize really well and then use access to really open up this horizon of probing high energy emission from these local universe sources.
Okay, we're a bit over time. Let's thank Aaron one more time. And now we have a coffee break. Back in, let's do 15. Okay. Thanks for the access shout out.
Yeah.
I'm trying to shout it out myself, but nobody can too.